Hello, curious chemists. Did you know amines are the social butterflies of organic chemistry? They love to form bonds, but their friendships depend on how many alkyl or aryl groups they hang out with. Today, we dive into how amines are classified based on those attachments. Amines come in three types: primary, secondary, and tertiary. That's one, two, or three groups bonded to the nitrogen atom. Think of nitrogen as a table with three chairs. How many people sit determines the amine type. In primary amines, only one alkyl or aryl group is bonded to nitrogen, leaving the other bonds for hydrogens. Secondary amines have two groups attached, and tertiary amines fill all three spots with alkyl or aryl groups, no hydrogens here. The general formulas capture this nicely. A primary amine is RNH2, secondary is R2NH, and tertiary is R3N, where R represents any alkyl or aryl group. Why bother classifying? Because these differences affect how amines behave physically and chemically, especially in hydrogen bonding and basicity. Picture a tree diagram showing each amine degree branching out with examples. That's how we visualize this classification. Understanding these categories helps chemists predict properties and reactivity. So next time you meet an amine, just count its alkyl friends to know exactly what type it is. Greetings again. Let's zoom in on our star player, the nitrogen atom in amines. Nitrogen here is like a social hybrid, literally sp3 hybridase, meaning it forms three strong single bonds called sigma bonds with either hydrogens or alkyl groups and holds on tightly to one lone pair of electrons. Imagine nitrogen like a pyramid, not quite the perfect tetrahedron, because the lone pair pushes the bond angles slightly tighter. In ammonia, the angle between the bonds is about 107 degrees, a bit less than the ideal 109.5 degrees, thanks to this lone pair's repulsion. This lone pair isn't just along for the ride, it influences the amine's behavior, affecting both its tendency to bond with hydrogen, that classic hydrogen bonding, and its knack for accepting protons, aka basicity. The shape is similar to ammonia, a pyramidal geometry that plays a big role in how molecules interact with each other. Picture a diagram showing the molecular orbitals and geometry of ammonia and amines, a pyramid with a lone pair at the apex and three bonds at the corners. This special arrangement is what gives amines their unique personality in chemistry. Welcome back. Now, how do chemists give names to our dear amines? Naming them is like calling out your friends by first and last names. First up, the common names, simple and friendly. You just name the alkyl group attached to nitrogen, then add amine. For example, a methyl group attached to nitrogen gives methylamine. But to keep things official worldwide, we use IUPAC names. Here, we replace the "e" ending of the parent alkene with amine. If the amino group's position matters, we indicate it by a number, kind of an address so no one gets lost. For secondary and tertiary amines, naming gets a little fun. We use an "-alkyl" prefix to show which alkyl group sits on nitrogen as a substituent, like N-methylenamine. Don't forget cyclic amines, which are named after their ring structures, like aziridine for a three-membered ring or piperidine for a six-membered one. Imagine a chart comparing IUPAC versus common names with structures laid out side by side. This helps you see how the system works in real examples. So whether you're writing a lab report or chatting chemistry casually, you're covered with these naming tools. Hey science sleuths! Amines are masters of disguise with their isomers. They show chain isomerism, where the carbon skeleton changes shape, position isomerism, where the amino group shifts its seat, and even functional isomerism, when they mimic other families like alcohols or ethers. For instance, A primary and a secondary amine might share the same molecular formula but differ by where the amino group or alkyl chains sit. Think propionamine versus isopropanamine. Functional isomerism is especially sneaky. Methylamine and dimethyl ether both have the formula C2H7N, but their chemical behavior and functional groups are miles apart. This shape-shifting ability isn't just trivia. It affects physical properties like boiling points, how soluble they are, and how they react chemically. Structural isomers can even belong to different homologous series, which makes studying them even more interesting. Picture the structural formulas of these isomers highlighted so you can spot where they differ. That's how chemists keep track of these molecular twins and cousins. Welcome back, molecule detectives. Let's peek deeper into the bonding secrets of amines. Nitrogen in amines uses sp3 hybrid orbitals to bond, meaning it combines 1s and 3p orbitals into 4 equivalent orbitals. Out of these 4, 3 orbitals form bonds with carbon or hydrogen atoms, while the fourth is home to a lone pair, our invisible yet influential guest. Because the lone pair repels the bonding pairs, the bond angles shrink a bit from the perfect tetrahedral 109.5 degrees to something a tad smaller. Each nitrogen-carbon or nitrogen-hydrogen bond forms by overlap. Think of it as two dancers joining hands at the nitrogen's sp3 orbital overlaps with the carbon's sp3 or hydrogen's 1s orbital. This bonding not only determines the molecule's shape but also explains important physical traits. For example, the lone pair's presence contributes to basicity and dipole moments, while the bonds allow amines to form hydrogen bonds that influence boiling points and solubility. Visualize a pyramidal structure with orbital overlaps clearly marked. That's the molecular choreography behind every amine. Let's put theory into practice with a quick example. Given the structure CH3NHCH to CH3, pause and picture this, a nitrogen bonded to a methyl group on one side and an ethyl group on the other. Your task is to classify this amine and give its IUPAC and common names. First step, count the alkyl groups attached to nitrogen. There are 2, a methyl and an ethyl, so this is a secondary amine because nitrogen is bonded to exactly 2 groups. For the IUPAC name, we look at the main carbon chain, which is ethane, replace E with amine to get ethanamine, and add a prefix N-methyl to indicate the methyl group is attached directly to nitrogen. So, the IUPAC name is N-methylenamine. The common name follows the simple rule, list alkyl groups alphabetically followed by amine, giving you ethylmethylamine. Imagine the structural formula with the methyl and ethyl groups highlighted. That visual makes it crystal clear. This example ties all our previous concepts together perfectly. Welcome, curious minds. Let's sniff out the physical side of amines, pun intended. Lower aliphatic amines tend to be gaseous at room temperature and are famous for their fishy odor. Imagine freshly caught fish but in molecule form. Aromatic amines, on the other hand, are often liquids or solids with their own distinct smells. When it comes to boiling points, the order is primary amines greater than secondary, which are greater than tertiary amines. Why? Because primary amines have more hydrogen bonding due to more available NH bonds, which bumps up the boiling point. Secondary amines have fewer bonding opportunities, and tertiary amines, having no NH bond, have the least hydrogen bonding, resulting in the lowest boiling points among them. Amines are soluble in water if they have 6 or fewer carbon atoms. This is due to their ability to form hydrogen bonds with water molecules through their lone pairs. The longer the alkyl chain, though, the less soluble they become because the hydrocarbon part resists mixing with water. Picture a chart showing boiling points plotted against amine type for a quick glance. These properties matter in everything from pharmaceuticals to perfumes because understanding them controls how amines behave in solutions and mixtures. Let's wrap up our amine adventure. Remember, primary amines have the general formula RNH2, showing one alkyl group bonded to nitrogen along with two hydrogens. Nitrogen's hybridization in amines is sp3, giving the molecule a pyramidal shape like a tiny three-sided tent. Naming amines follows the IUPAC rule, where you replace the ending of the alkene with amine, and for substitutions on nitrogen, add an enalkyl prefix to keep things crystal clear. Lastly, when it comes to boiling points, primary amines top the chart, followed by secondary and then tertiary, thanks to the decreasing ability to hydrogen bond. These essentials form the foundation to understanding amines in both the classroom and real-world chemistry. That's it for today's concept. Chemistry is always more fun when you can laugh, learn, and picture molecules dancing. See you in the next session.